Unfortunately, in practice, this is not really how it's taught. So in practice, you get this. And this is also what happened in the 1950s and 1960s. People started saying, well, you cannot do t-tests if the data aren't at the interval level of measurement. It's wrong to do that, and it's bad to do that, and things will happen, and psychology will die, etc., etc. And there were whole police forces set up to enforce this. Here's an example of the measurement police that writes out, and these people started writing all kinds of books about how you shouldn't do that, and how you should attend to measurement level, and how you should, never do t-tests on ordinal data. And they were getting also a bit on the turf of the statisticians, because for you it's all the same thing, right? You are like, it's your out group, so you don't see the differences. But for me, these are completely different people, right? You have measurement people, statistics people, nothing to do with each other. So the statisticians, they are like this, right? They are very, very angry. If you are in a room with statisticians and you bring up the notion of a measurement level, you got to duck, right? Because they are very aggressive. Statisticians are very dangerous people. And the statisticians because statisticians say, I don't care where these numbers come from. In the whole derivation of a t-test, there's a mathematical derivation of a t-test. Nowhere in that derivation is an assumption about the skill level of the variables. It just says you need to have continuous variables with equal variance, and that's it. Normal distribution, but not something about the quantitative skills. So, go home with your measurement levels, and I will execute t-tests on any data I choose to execute t-tests on. I don't let you measurement folks decide what I, as a statistician, am allowed to do. Who do you think you are? And that is where this weird paper comes from, that I find one of the beautiful methodological texts that exists. Basically, the statistical treatment of football numbers exactly makes this particular point. It is written as a piece that ridicules basically the normative interpretation of measurement restrictions on your statistical work. And Lord was a statistical person, but he also did a lot of measurement, interesting guy. And he wrote this very short paper on the statistical treatment of football numbers. And the idea of the paper is, you've got this professor, a measurement theory professor, and the measurement theory professor, he never, ever would execute a t-test on ordinal data. He would never do that because, that was against everything he stood for. And he retired at some point, but he really liked numbers. He loved to work with numbers. And so the university, when he retired, gave him something to do. That's what they often do with emeritus professors. They give him something to do. He could assign the numbers on the backs of players to the teams. So everybody would go to the professor and get a number. And the professor actually made a whole machine that would give out these numbers. So you came there as a new student, and you would get a football number. You would put a coin in, and you would take out your T-shirt, and you would say, I've got number 9, right? And so that's what the professor made. But then at some point there was a dispute, because the freshmen, so the first year students, they came at the professor with a complaint. They said they got too low numbers. And the sophomore people, so the second year students, got higher numbers. And they suspected that somebody had been tampering with the machine to give the freshmen lower numbers. What to do? The professor heard the complaints and looked at the numbers and thought, I don't know how to to deal with this. I mean, they're just numbers on the backs of the players. They're nominal numbers. I can't do anything numerical with this. So how do I decide? Higher or lower has no meaning for numbers on the backs of players. It means nothing. It's a nominal skill. I can do anything. So what he did was, he thought, well, you know what? I'm going to ask the statistician. And he went to the statistician who was on the other side of the hall. He said, I've got this machine, it gives out numbers, but the freshmen claim that there has been tampering with the machine and that they got lower numbers. And, you know, I'm sitting with these nominal numbers and I cannot do anything with nominal numbers because I'm not allowed to do anything with nominal numbers. And then the professor, the statistician, he knew the story of the poor professor's resignation from teaching and said, well, that doesn't matter. And when the problem had been explained to him, he chose not to use the elegant non-parametric methods of modern statistical analysis. He just took the professor's list of football numbers, and there's a lot of them, that's not really important. 100 quadrillion, this is to satisfy infinity stuff, doesn't matter. And what he did is he added them. He added all of the numbers together and divided them by 100 quadrillion. And he said, well, the population mean of all your football numbers, all of them that you have, is 54.3. But these numbers are not cardinal numbers. That's quantitative numbers. The professor expostulated, you can't add them. Oh, can't I? Said the statistician. Well, I just did. Furthermore, after squaring each number, adding the squares and proceeding in the usual fashion, I find the population's standard deviation to be exactly 16.0. But why? They aren't even ordinal numbers like test scores. Well, the numbers don't know that, said the statistician. And since the numbers don't remember where they came from, they always behave the same way regardless. And the professor gasped. And what does this illustrate? What is the point that's being made here? I have to finish the story. So the story is, what the statistician goes on to do is a t-test basically, and showing that yes, indeed, the numbers of the freshmen are significantly lower than those of the sophomores. And so probably the machine had been tampered with. So he treats these nominal numbers as, he just puts them in a significance test, and he draws a sensible conclusion from that test. What is the message?
Maybe it depends on the kind of question you try to answer.
Exactly, it depends on the kind of question you want to answer. And the question that the professor has here is not a question about the nominal nature of the numbers. It's a question. It's about the frequencies with which these numbers arise. And the question is that a particular kind of numbers is less frequent in one group than in another group. And so it's about the distribution of these things. So, in other words, in some cases, at least in this one case, and it stands, everybody knows this paper in methodology and statistics, it stands as a case, you know, a proof of principle. There's no general thing that you can really conclude for this, but it shows that there are exceptions. There are exceptions to these norms, and there are cases where you can actually draw sensible conclusions from illegal statistics. So prohibitions like don't run t-tests on ordinal data are not always justified. It's not, these laws are not carved in stone, they depend on the situation. They depend on the pragmatics, on what you want to know, what kind of information you have, and especially on whether you know what you are doing. And that is why these methodology and statistics classes are so important. Because if all goes well, they teach you what you are basically doing. So you're not clicking the buttons like a monkey. P is kleiner than 0.05. The effect is real. No, you're thinking about these things sensibly and responsibly, and you're always weighing in the pragmatics of the situation. What do you want to know? What do you already know? What does this add? What are you prepared to invest in the data? Yeah, the answer is here. The question is here, isn't there a way for the professor or for this to be turned into a sort of legal way? Isn't there a way of framing this problem such that it is actually in accordance with Stevens' rules and that there is actually a quantitative structure under this? That's a good question. My personal opinion is yes. I personally think the thought experiment is not a valid counterexample because the actual test has nothing to do with the players but with the machines. So the hypothesis is about whether the machine has a certain level of bias, and that is a quantitative property. But that, even if that's true, the point still stands, right? You gotta always, you should not mindlessly follow rules. So I can give you an example of when it can go terribly wrong. One of the things, so a very, very, very few people would be inclined to defend that the distances between psychological scale points have meaning. So that the differences on, say, a neuroticism test or something like that have meaning. Most psychologists would say, well, it's an order at best. Now, if I put these things into a design, and I have, for instance, a cross design, so I have two factors, say male, female, an experimental condition or a control condition, and I get an interaction effect, but it's not crossing. So it's like this, the control condition, experimental condition, and these are the males and these are the females, and this is some test. Your level of empathy or whatever, empathy, let's say empathy, popular thing right now. Can also be some fMRI stuff, doesn't matter. It's anything that doesn't have a strong quantitative interpretation. Your hippocampus lights up when you do something. That's all, that doesn't matter. So now you find this, then I know there's a theorem that says that if these things don't cross, so it's not like a crossing interaction, no crossing interaction, then I can always transform this away with a monotonic transformation. That's allowed, right? So this is a big thing because non-crossing interactions are sort of like, they make up like a very big part of psychology, and it means that you can transform away all significant effects that have this form. So that's potentially a very tricky thing to have in psychology. And then it can really matter, because big conclusions can hinge on this, right? So like, females do better with multitasking. Oh yeah, so there's lots of examples of where you use illegal statistics and it works out fine. I do it every day. Before breakfast, do an illegal test. It's good for the elasticity of the mind. No, seriously, I always do Pearson correlations on the dichotomous data. No problem. Yeah. If you know what you're doing, there's no problem. I wouldn't advise it for everyone here because I sort of have a feeling for what these things do. So I know what I'm doing. I'm not. But if you don't know what you're doing, it's probably safer to stick with the SPSS rules. But this works. I can easily come up with all kinds of hypotheses that you could test by illegal statistics. Maybe you have to shift your interpretations a bit, but a lot is possible. But we keep most of things in check. So if you go by the rules of SPSS and you don't do t-tests on nominal data, then there is a lot of validity threats that cannot hurt you. Right? So that's the function of these things. But if you want to live dangerously and execute t-tests on dichotomous variables, you don't have to close the door. Okay, so the moral of this story is that if you know that even though there are strong arguments for Stephen's position and the admissible test statistics position. And there are also good reasons for normal people to abide by these rules, because that saves them from a particular kind of trouble. It's never a all or none issue, right? So there are always exceptions. And how do you actually deal with this? I personally am often in the situation where I'm dealing with this. So what I always do is I love the concept of robustness. If I have a certain claim and it depends on certain scale values, then I will just transform them back and forth. You know, I will take the square root, I will take the square, or and I will see whether my conclusions are robust against these transformations. And if they are, you know, I'm okay. And if they're not, I have an interesting question to answer, namely why. But very often these things are actually robust. Okay, so take-home message. Methodological rules are not written in stone. They are man-made, they are based on assumptions, they are based on arguments. You can question the arguments, you can challenge the assumptions, always. It's a ground rule of science. All assumptions can be challenged. Also, under the tapestry of the Field and SPSS book live all kinds of exotic methodological animals, some of which are pretty dangerous. Most of them we keep in check. So, for instance, all of these ordinal dangers, the dangers of transformations, are kept in check if you just go by the rules and do non-parametric tests on ordinal data. Then these animals are caged. So that's, but it's good to know that they exist, and it's also good to know a little bit about what they eat. And should you be interested in further study of exotic methodological animals, then you're most welcome to study in our department. We have a department, we have a specialization, psychological methods. Maybe you thought that's really nothing for me. Well, there's a lot of interesting stuff in methodology, so feel free to drop in. I hope you took something home with this, and well, see you next time.